Pepe's World, the show for computer hackers and electronics enthusiasts with no money and no friends. It's part 2 of our series on how to zap a burglar in the nuts if he tries to steal your motorcycle. In this episode we're going to be learning how to write the software. So let's get started. Wait a minute, I can't use that catchphrase, can I? That belongs to someone else. Shit. I know. What about Pepe's World? Think, McFly, think. Anybody home? How are we going to program this fucking thing? Well, first of all, we're using an AT-Tiny85, not an Arduino. But what we do is we use a little board like this, which simply connects up the Arduino's SPI pins to the AT-Tiny SPI pins. And we follow a little guide which allows us to install support for the AT-Tiny85, which I will link in down below. And that allows us to select a couple of these AT-Tiny85 chips and also select the internal clock speed, which is actually pretty fucking awesome if you think about it. Alright, so what the fuck were we doing in the first place? Alright, well, we have a motorcycle here, and there's that fucking fly again that I don't want to have stolen. So we've got an AT-Tiny85 in there, which checks to see if the power is on, because only I can do that, being the legal key owner. And we've got some wires here. We've got the capacitive touch, and we've got the 400,000 volt zapper. When the capacitive touch determines that someone is touching the damn thing, and the power is not on, g'day, then 400,000 volts goes through. Now, unfortunately, there is a caveat. When 400,000 volts is touching this bike, the capacitive touch simply does not work. Something to do with electrifying the surface. Now, what also happens is the power regulator gets very fucking hot because I chose a stupid one. Actually, I burnt out my original one. You didn't see that in the first video. So what we need to do is we need to have 3 separate modes. One where the touch sensor is working, one where the zapper is going, and a third one where nothing is fucking going. So the power regulator can cool off, and so the seat can go back to normal, right? Because that takes a little while. I don't really know physics. So on the touch mode, we sniff the seat with a capacitive touch. We determine if we've got a good signal, and we also eliminate false positive signals, which we'll look at in a second. And if it determines that it's a real signal, then we go into zap mode, and then goes into dead time, and then back to touch mode. Safety first! Okay, safety features. First of all, we've got some audio warnings. Now, because an AT-Tiny85 doesn't have all the pins in the world, I doubled up some pins. The transmit pin, which goes off to an attached serial terminal, is also split to go to a piezo transducer, which means that when I send letters to the terminal, oh, would you fuck off, fly? Jesus! Now, it's important to give the thief a bit of warning. This delay also doubles as some time to get rid of some false positives. You should limit the amount of time that you're zapping, because that lets the thief actually get off the fucking bike. And don't zap them constantly. If you're zapping constantly, then there's a good chance they won't even be able to hop off the bike. They won't be able to use their muscles properly, especially if it's on their balls. Ah, crap! And have a good 10 seconds dead time afterwards. And it helps to have some feedback, just so you can know that the thing is working. There's something about having 400,000 volts sitting underneath your ass, and you just want to know if it's working or not. Fuck out, I'm trying to record a video. Let's go have a look at the code. I know this might scare the shit out of some people, but don't worry, we'll walk through it. We'll go through it step by step, and we'll make sure you understand fucking everything. Because if you don't, I'll come to your house and I'll kill you. Okay, so first of all, shit's pretty straightforward. We need these libraries. The capacitive touch sensor library, and we need the software serial library. The little AT-Tiny85 there, he doesn't have a serial port. So we have to fake a serial port. No shit, you can actually fake having a serial port. It's called bit banging. After importing our libraries, we just define our pins, and we define our modes. Now, what are these defines? What does this mean?
Pepe's going to teach you some C!
In the program, this isn't actually a variable. No shit. What happens is before this gets compiled, a program called a precompiler will go through the source code and literally replace all the instances of brakes pin with the number 4. You do this for when you don't want to change a variable afterwards, and because you're not changing anything, it doesn't really vary, so it doesn't have to be a variable. And we save memory. Okay, so now that the setup routine is started, create a software serial object, and we create a capacitive touch object. And these objects take arguments for which pins they use. Check last episode for an explanation on how the fuck that worked. You have a drive pin, which changes on and off, and you have a receive pin, which is basically kind of connected to the send pin, but through U, and it treats U as a low-pass filter, which really affects the amount of time that the drives pin will have its changes manifested on the receive pin. So, our startup routine. Wait 10 seconds for me to put the fucking seat down because I'm slow. Calibrate the touch sensor, and proceed with the main loop in touch mode. Awesome! And at each stage, it'll do some beeps. Now after 10 seconds, we send out an audio warning and we go into our capacitive touch calibration. Now this is the only difficult part of this whole fucking thing. Now these are our variables to do with touch calibration. We've got the acquire time in milliseconds, which is how long we'll be sniffing a strong signal for to watch it die down and reject it as a false positive. Now after 2 seconds, this is when we start beeping at the user. Because we're using this time where we're determining a false positive, it's also a way to give the potential thief a bit of a warning time. And this here is the threshold.
Pepe's gonna show you some theory.
Let's just say you get a signal that looks like that when no one's sitting on the bike. You could consider this your baseline in a couple of different ways. You could look at the loudest signal that you've received and go, okay, anything above this I will consider a strong signal. However, you might notice that this is only a transient spike. Most of the time, your signal is going to be below that. If you're thinking the way I'm thinking, that's wasted dynamic range. What you really want to do, if you're cool like me, is forget that and look for the average signal. And that's simple enough to do. We iterate through, say 50 odd times, and we keep a record of the largest value we've seen and the smallest value we've seen. And after all of this, to get the average, you divide by the number of scans that you've done. Now, if you look closely, I put a delay halfway in the middle of all of this. By having effectively 2 calibration sweeps half a second apart, it'll actually give a good rejection for lower frequencies which are upsetting the average. Alright, I have this baseline signal, but I'm going to have noise which is above that. Noise which goes up to about here. What we consider this to be is the noise floor. Now, if your memory is more than a couple of seconds, you would have remembered that I said that most of the time the signal is below this peak. So what we generally do to make things simple on ourselves is we offset everything by the baseline. What we want to do is we want to make sure that the signal is above about here for a decent amount of time, because this gives us all of this extra range. What it also lets us do is get a realistic scale of what's going on. And I just determined this 50% value through experimentation. I could actually raise or lower that to determine my sensitivity. We don't have to hard code any numbers. Everything is dealt with as a percentage or a fraction. And that means we can use the same math for different environments. All we need to do is calibrate it initially using this math. Now we've considered our baseline average. Sweet, no problem. We do a couple of beeps and the main program starts. Now, we are in touch mode, so now our responsibilities are sniffing the seat, and on a strong signal, spend a wee while removing the false positive, then we go into zap mode. Now let's have a look at the code for that. So it's pretty straightforward. We record the time that we started here for reasons which you'll see in a minute. So our primary responsibilities are to check if the seat is occupied and if we don't have legal power, which is my word for if the brake light is on, right? Now let's have a look at the seat occupied routine. Now this is where we're dealing with the touch calibration sensor, taking into account the calibration that we did. And it's pretty straightforward. Considering that we've known ahead of time the average value and the expected noise, we can simply return true if the sensor has registered a signal significantly above the average. And how do we determine significant? Well, we look at the noise floor, because we've got the ability now to compare the size of the noise to the size of our signal relatively. So we can say that our signal is twice as strong or 3 times as strong or whatever it is. So we read a value from the touch sensor. We look at the adjusted value. This is where we're offsetting shit down to here. So this noise threshold value, what that translates to here is 50% along there. If the signal goes above there, then we consider it a strong signal. But Pepe, what the hell is this? Well, that's a timeout for the touch sensor. Like I said, this thing does timing, right? That timing could go out for fucking forever. So you have to set a timeout limit, right? If you have a very sensitive touch sensor and you literally touch the damn thing, it'll return -2. It's just what it's programmed to do. But what about rejecting false positives, right? Well, this is the cool shit.
Extreme mathematics.
What we do is we loop for a couple of seconds and we look to see if the signal ever drops below this halfway mark, right? Because if it does, then we know that we've probably got some noise going on, right? And it's probably just a fluctuation, which we know will happen. While we still consider the signal a possible naughty signal from a naughty person, and while the time is less than 10 seconds or whatever the fuck it is, we look for reasons to consider it a false positive. Is the legal power on? I.e., is it me and I've just sat down and it's taken me a little moment to turn on the fucking key? Or the signal has gone below the threshold. Or, and this is a goodie, the clock is rolled over. If you're doing calculations based on milliseconds since boot, which is what that millis function returns, it'll actually loop back around to 0 again. Not kidding. And that will screw up all of your mathematics, which is why you should always check for clock rollover. If you don't, you'll die. You will just die. In fact, people have probably died from not checking a clock rollover. And how do I check for clock rollover? Easy. I've recorded the amount of time since boot that an event happened, right? You look at the clock, and the time since boot is less than that, i.e. the clock is now in the past. Think, McFly, think. Okay, so after all of this, if we haven't determined the signal is a false positive, naughty will still be true, and thus we change our mode to zapping mode. Now this is where shit gets sexy. Okay, so the zapping loop. This is where we're periodically zapping for about 8 seconds or whatever it was. Was it 5 seconds? Who cares? We record the time that we went into the zapping mode because we need to check for when we've been there too long. We announce to the user that we're in zap mode. We start bleeping, and this is the easy routine for only doing the periodic zaps. If I want to zap for only the first 100 milliseconds out of every 800 milliseconds, I simply do modulus 800. Easy, right? For every millisecond on the clock, the result of this calculation will go 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 799, and then roll over back to 0 again. And all we do is check if we're in the first 100 of those milliseconds. That's it. And the result of this is a Boolean, and that gets sent to the digital write routine. Now while in zapping mode, if somebody turns on the key, me, then we stop zapping, right? Or if it's simply time up. If I don't check for clock rollover, I don't think this thing would ever stop. Or would it? I'd have to think about that. Come on, you little prick. And now we turn our mode to dead time, and of course we turn off the fucking zapper. Now this means that the program's going to exit zap mode, and it's going to go back up through its main shit, come all the way back down again, and do nothing. We just wait for the regulator to cool down, and we wait for the touch sensor to cool down. But what's this third thing? Detect mangled touch sensor if possible. Well, if the touch sensor is actually having a bit of trouble, which it will, I determined through experimentation that it actually times out and often does simply return -2. So that's why in our dead time loop we have this clause where if the raw value from the touch sensor is -2, then we simply restart our wait time over again, which is a safe thing to do. Simply keep waiting until the touch sensor has stopped being an idiot. And of course, if we've been waiting for a long enough time, then go back into touch mode. Straightforward. And of course, we've got our mandatory check for a clock rollover. And at the end of dead time, we simply report how long it's been. And we go back to square one, where we're sniffing the seat. And shit goes around and around. And that's it. This has been another episode of Pepe's World, a show for computer hackers and electronics enthusiasts with no money and no friends.
Raspberry Pi, Arduino, YouTube, 3D printers and drones. Like, share, and subscribe.